I would like to begin with clickers. We'll review what we just discussed and build on it some more. I hope these questions help you solidify your knowledge. I see. Oh, that's what he wanted me to know. Okay. Do they help? Good. Okay, good. So I have several today. See if we got what we just learned. Okay, go. Talking about electromagnetic waves, the whole spectrum, light, not just visible light. One of those is not part of that. Which one? Oh, really? Why does it keep kicking me off? Sorry, you users, you're going to have to switch your session ID number. Although it kept the responses, maybe you don't have to for this question, but the next ones. That's been happening more in the last few weeks, hasn't it? I'm going to talk to the software folks, see if they got a reason for that. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Has everybody had a chance that? Okay. 80% said B. You're right. Remember, there's a difference between sound waves and radio waves. Radio waves is part of the electromagnetic spectrum. It has an oscillating electric and magnetic field. That's how your radio gets reception. That's how the information gets to your radio. The antenna, the waves come in and the oscillating electric field makes the charges in the antenna move. And you can tune with resonance what station you want. And then what's it do? It sends another signal to your speaker and makes it move to push the air around so we can hear it. And that's sound waves. So they're different. All waves have a source. What's the source for electromagnetic waves? Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, some of you think energy fields, and most of you electrons. Well, those energy fields come from the electrons. That's the ultimate source. What's it say down here? It may be said that light is transmitted by vibrating energy fields. That's true. That's how they're transmitted, through the vibrating electric and magnetic fields. But that's not the source. That's not what caused them. Does that make sense? So those wonderful electrons in all our atoms making all of us up. Okay. I love when you push the wrong button thinking you're in one program when you're not. Oh, I'm sorry. I hit the correct button in the wrong program. All right, go. Talked a lot about driving frequency and resonance last time. It has to do with sound waves, but all waves. See who remembers this. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you think ultraviolet. You're correct. We'll review this more. That is glass's natural frequency for those electrons. Thus, they get absorbed. And glass is opaque to ultraviolet light. Visible light goes through. It's at a different frequency. It drives the electrons, but it doesn't make them resonate. That's not their natural frequency in glass. So they re-emit and it transmits through. It's transparent to visible light. We know that. Ultraviolet resonance. They get moving a lot. And it gets absorbed.
A serious question.
Good, I like serious questions.
So this kid once told me that you can't get sunburned through like a car window or a window.
You can't get sunburnt through a car window. Now, most glass, this is true. There's some types of glass that does let UV, ultraviolet light, through. If it can get through, if it's transparent to those frequencies, you'll get sunburnt. And I know my father-in-law has. You'll get a lot less burnt, though, if your window's up versus it down. And that's because it absorbs a lot of UV. But all glass isn't made the same. And so some UV might be getting through to sunburn you.
What about like UV protection in sunglasses?
Yeah, UV protection in sunscreen, sunglasses. There's a coating on my glasses, a UV coating. Sunscreen, your lips, chapstick. Yes, there's the pigment in those materials that naturally, the electrons in that want to naturally vibrate it with UV. So it gets absorbed instead of passing through to your skin or eyeballs and damaging you. That's the point of that, of sunscreen. Is there a hand?
Yeah. So you said radio waves can be creating electromagnetic field, and then that when it hits the speakers, it creates the longitudinal waves, and then that's how we hear sound. Can you create sound out of visible light if you have a high enough amplitude?
So how radio will pick up radio waves and convert that to sound waves? Can we do the same thing with visible? Or any other spectrum? Yeah. Theoretically, yes, absolutely. What a radio does is it tunes to those specific radio waves from your favorite, FM station. So if we could tune to a different frequency, different station, right? What if we could tune completely into the visible range? Well, certainly you could. If you find that resonance, then yes, it'll make, yes, you can do the same thing.
Much higher frequency for that?
Visible light is a lot higher frequency than radio waves. Yes. But theoretically, you could do that. Yeah, you could take light and convert it to sound.
So how is it that it's actual, it's not just guttural sounds, like static, it's actual words or...
Oh, how do we get it? So, yeah, we weren't covering this, but there's two types of radio, FM and AM, frequency modulated and amplitude modulated. What they do is they use a carrier wave, the frequency of the radio wave that transmits it to your radio or your iPod or whatever. That's what gets it to you. On top of that signal, they piggyback another signal that modulates it. And it's that modulation frequency that's telling the speaker to move at that rate. And if the speaker moves at that rate, we can hear it. That's the sound. So we're not hearing the radio waves. We're hearing the piggyback signal on top of it that modulates it. And that's what drives the speaker to move the air around to sound waves.
So how did they, pick the frequencies that they did?
Why did they use them? I don't know completely. But my guess is, one, radio waves are longer. And which ones transmit farther? Low frequencies or high frequencies? Low, because there's less interaction, so they can go further. That helps. And that part of the spectrum was open. It's getting crowded now. You get cell phones. You get a new cell phone. Oh, you get Wi-Fi. There's about every band is taken up for something now. TV, that was easy when TV came. Oh, we got this big old band. Well, we're going to use this part of it, range. Radio waves will be for that. cable can be for this. Cell phones can be for this. Well, it's getting narrower and narrower. There's less real estate out there on the electromagnetic spectrum to tap into. But I think it was open and convenient. Good questions. Make sure I'm getting the right one. Okay, go. So visible light that shines on a pane of transparent glass. What's it do? We just did ultraviolet light makes the electrons resonate. Visible light does what? So the book does a lot of those analogies while you're thinking, and I interrupt you and distract you. The analogy of like, here come the radio waves, and you put up an antenna to intercept them and get the signal out. You can think of materials like glass as like little antennae. Antennae. And so here come the electromagnetic radiation, and it makes the atoms vibrate. They're like little antennae. And some are at the resonant frequency, and some aren't. Oh, where are we at? 26. 10, 9, 8, 7, 6, 5, 4, 3. Hey, we've gained people. 2, 1. 91A. Very good. It produces a chain of absorptions and re-emissions through the glass. And that's why it slows down, that time delay to be absorbed and re-emit. So on average, through the glass, it's going to go more slowly. By the way, which one does UV do? Ultraviolet light on glass does which one? I've heard a few responses. See, this is why we use clickers. I just didn't prepare this one. I thought of it right now. C or what?
Or D.
C or D? Well, I'm hearing them more C's than anything. That's what I'd pick. So it makes them resonate because they vibrate more. More of that energy is converted to thermal energy. If it's completely absorbed, it's C. So it'd be entirely the thermal energy, and none of it would pass through, and you wouldn't get sunburned. But let's say you get slightly sunburned, maybe B. No, that's not right. There's no answer for that. It's just a lot of it would be converted to thermal energy, but not all. A little bit might get through. Maybe that's why I didn't ask it. This is fun. I love these questions. All right. Light does not pass freely through opaque materials, or light that does not pass through freely through opaque materials is what? See how they build? I hope you get this one now. Remember what opaque is, and it doesn't make it through. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, good. Most of you guessed A. Yeah. If it doesn't make it through, and it's opaque, it's not very reflective, and it didn't transmit through, it's not transparent, where did it go? Conservation of energy. It was converted to thermal energy. Internal energy. That's a better term. Okay. Enough of the clickers. You can put those away.
I have another question.
Yes, ask away.
How come some light bulbs are like clear and other light bulbs are not so clear?
Some light bulbs are clear and some aren't. It's the coating on the glass.
Yeah, but
Glass is transparent, but if they put like phosphors or a coating on it, and that scatters the light. So it can hit it and scatter in all directions. It's diffuse. So it's semi-transparent. Alrighty. I want this picture. Guess I should have left the lights off. So here's a nice analogy the book has. I like this picture. So upper left. The light wave comes in, and an electron, or an atom, absorbs it. Gulps. It gulps it up. So we can walk through this step. So in it comes, and it's absorbed. Makes the electron, it now has the energy. It gives it up, re-emits a different photon of light at the same frequency, because it was made to resonate at that frequency. Resonate at that frequency. That's what it vibrates at. That's the one it gives off. Goes to its neighbor. Loop. It vibrates, burps it back up, and so on. And that's what takes time, and why we say light slows down through a material. It still travels at the speed of light here, here, whoops, and here. But this process of gulping and burping take a moment. My daughter would like this potty humor. So remember that analogy. I wanted to show that to help you. All right, color. Then we'll come back. I love color. Oh, right. We were right at shadows from the last chapter. So I'll do that first. Let's make a shadow. This isn't too complicated. Let's turn on a light source. We'll project it onto this screen. Ta-da! You guys know what shadows are. I'll hold this up. So it blocks the light. This is opaque, so it absorbs it. It's turned into internal energy. It's warming it up slightly. The light cannot make it to that part of the screen, so it's dark. But look at the edges. See how it's a little fuzzy? That's because this light source is not a point light source. It physically has dimensions of physical size. So light from one side of the light bulb might be getting blocked. But light from the other side of the bulb might not be blocked. So it's partially blocked. So these have names. The part where it's all blocked there is called the umbra. The umbra. And these are in your book. It's a complete shadow. But this little fuzzy region where it's partially blocked, a partial shadow, is called the penumbra. Am I pronouncing that right? They get used so much in everyday language. Yeah. The penumbra. Penumbra. There's no R at the beginning. So umbra and penumbra. Umbra and penumbra. Partial shadow. So like here, right here. Light from the top of the bulb can reach there, but light from the bottom of the bulb is being blocked. Does that make sense? If you're closer to the screen, less of the light gets around it, and you get a sharper shadow. Do you see how the edge is more crisp? The penumbra is smaller. It's just because light can't get around to form as big a partial shadow. And if you're far, it gets fuzzier and fuzzier because it's easier for more light to get around it to that part of the screen. Now, if we switch light sources to a point light source, this is a little itty bitty LED. Now the shadow is quite crisp, and whether I'm close or far, if I get really, really, really close, we can start seeing it, the penumbra getting a little fuzzy there for the same reason, because the LED still takes up a little bit of space. But the smaller the light source, the cleaner the shadows. So we're going to play more with shadows, with color. But what's fun is eclipses. You can explain eclipses with shadows. Oh, I'll just leave it up. It's up there. Here's a little animation your author created. So if the sun is on the right, you can see the Earth and the moon the moon orbits the Earth. Okay, technically they're orbiting their common center of mass, but whatever. And they cast shadows. When the moon moves into the shadow of the Earth, we call that a what? A lunar eclipse. Yeah. Easy enough. When the moon is in between, it's coming up, the Earth and the sun, the light is blocked. And we call that the new moon. That's when you don't see the moon, the new moon. It's dark. As it keeps going around, we start seeing sections of it. You get the phases of the moon because different parts of it are illuminated, reflecting light back to us. As it comes around and gets into our shadow, two things can happen. A lunar eclipse, if it falls in our shadow. But if it doesn't fall in our shadow, because it's a little higher or lower, we call that a full moon, because we'll see the whole thing. I got a different animation for that. Oh. I accidentally closed it. Silly me. That's chapter 20, right? Oh, I love how he labels them all the same, so I don't know which one it is. Let's just open them all. Nope. Nope. Thank you. I'm in the wrong chapter. Multimedia, interactive videos. Here we go. Sorry, I thought I already had this one open. Nope. 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 Oh, he had it. Okay, it's not that. It's not that. Not that. Not that. Not that. Not that. Oh, fine. Instead of wasting more time, look at me. You don't need animations. So, if this is the plane, and the sun is right in the middle, or the Earth is right in the middle, and the moon's going around it, then when the Earth is or the moon is over here, it'll get blocked. That's a lunar eclipse. So Earth, moon, they're in the same plane. It's blocked. But what happens most of the time is the moon isn't going around in this plane. It's like 5 or 10 degrees a little lower, so it like comes down here, crosses the plane, comes up above and down. And that changes as it precesses, like a top, it kind of wobbles and rotates around when that happens. So most of the time we see the light. Because if it's up here, the sun can get it. We see the full moon. But when it's aligned right with it, it's in our shadow, and you get a lunar eclipse. That's all the animations show that I can't find at the moment. So, this one is here's the moon shining on the Earth, and you can see the umbra is the dark part of the shadow, and the penumbra is the partial shadow. So if I click right here down in southern South America, this is what you'd see during this eclipse. What's different about this eclipse from what we were just discussing? It's still an eclipse, but we don't call this one a lunar eclipse. Did you notice? This is a solar. This is when see the sun rays are over here on our left. And that's when the moon gets in the way. And the moon blocks out the sun. But if you're down here in this part of South America, you don't see it because you're not in the shadow. The moon is smaller. Right? But what if you're like right here in the penumbra region? What do you think you'd see? A partial solar eclipse. It might look like that. Yeah, you'd see part of it blocked because some of the light from the other side is getting to you. You're in the penumbra. It's a partial solar eclipse. And only those lucky people right there-ish, whoops, there, would it block the whole sun perfectly. That's a solar eclipse. And there's a very small portion where that ever happens during a solar eclipse. Most people see a partial, like this, or not at all, because you're in the wrong spot at the wrong time. But it's just that play around with shadows and where you're at. So I found this. Let's get some audio up here, because this is coming up.
A tetrad of lunar eclipses, presented by Science at NASA. For people in the United States, an extraordinary series of lunar eclipses is about to begin. The action starts on April 15th, when the full moon passes through the amber shadow of Earth, producing a midnight eclipse visible across North America. That night marks the beginning of a lunar eclipse tetrad, a series of 4 consecutive total eclipses occurring at 6-month intervals. The total eclipse of April 15, 2014 will be followed by another on October 8, 2014, and another on April 4, 2015, and another on September 28, 2015. The most unique thing about the 2015 tetrad is that all of them are visible for all or parts of the USA, says longtime NASA eclipse expert Fred. On average, lunar eclipses occur about twice a year, but not all of them are total. There are 3 types. A penumbral eclipse is when the moon passes through the pale outskirts of Earth's shadow. It's so subtle, skywatchers often don't notice an eclipse is underway. A partial eclipse is more dramatic. The moon dips into the core of Earth's shadow, but not all the way, so only a fraction of the moon is darkened. A total eclipse, when the entire moon is shadowed, is best of all. The face of the moon turns sunset red for up to an hour or more as the eclipse slowly unfolds. Usually, lunar eclipses come in no particular order. A partial can be followed by a total, followed by a penumbral, and so on. Anything goes. Occasionally, though, the sequence is more orderly. When 4 consecutive lunar eclipses are all total, the series is called a tetrad. During the 21st century, there are 9 sets of tetrads, so I would describe tetrads as a frequent occurrence in the current pattern of lunar eclipses, says Espinac. But this has not always been the case. During the 300-year interval from 1600 to 1900, for instance, there were no tetrads at all. The April 15th eclipse begins at 2 a.m. Eastern Time, when the edge of the moon first enters the amber core of Earth's shadow. Totality occurs during a 78-minute interval, beginning around 3 o'clock in the morning on the East Coast, midnight on the West Coast. Weather permitting, the red moon will be easy to see across the entirety of North America. Why red? A quick trip to the moon provides the answer. Imagine yourself standing on a dusty lunar plain looking up at the sky. Overhead hangs Earth, night side down, completely hiding the sun behind it. The eclipse is underway. You might expect Earth seen in this way to be utterly dark, but it's not. The rim of the planet seems to be on fire. As you scan your eye around Earth's circumference, you're seeing every sunrise and every sunset in the world. All of them, all at once. This incredible light beams into the heart of Earth's shadow, filling it with a coppery glow and transforming the moon into a great red orb. April 15th, and let the tetrad begin. For more rare occurrences in the night sky, stay tuned to science.nasa.gov.
Cool, huh? Well, you know where I'll be April 15th. Staying up late watching the total lunar eclipse. So it talks about how they're blood red quite often. Now we can get more into color. Let's talk about how colors work. Your basic sum up is colors of light have different frequencies, different wavelengths. And so they resonate materials differently. And so if, like his red sweatshirt, that means red light is coming into my eye. It's that frequency that's reflected off of his jacket. It's not emitting light, right? It's not glowing red. We're not talking about infrared light here. Visible light. Where's the light come from that bounces off of his jacket? Yeah, the room lights. So there must be some red in those white lights because it hits his jacket, reflects off of it, and bounces into my eyes so I can see red. Likewise, green. There must be green in this white light. Blue. I see all colors. White light is composed of all colors. Let's show that with a prism. We'll take white light from this projector, shine it over there on the wall. You guys can tell it's white because our brains are smart, even though it's reflecting off of a red wall. Okay, so now I'll put a prism in front of it. And what's a prism do? It refracts the light waves. It slows down when it goes through here because it's getting absorbed and burping. Gulp, burp, gulp, burp. And in doing that, though, because it slows down, the wavefront rotates. It bends. It refracts. And if I refract it at the right angle, there we go. Over here on the screen, you can see the colors spread out, and you can tell which colors make up this light source. White light's made up of all colors. But the reason it spreads them out is because which one of these, you can reason this through, which one of these light waves travels faster through glass? We got some votes for the purple? Yeah, think of the wave coming into the glass, right? And the one that's in the glass, this half, goes faster. So it bends. It's going to bend more. It's going to have a larger effect. Purple has a higher frequency, more energy, shorter waves. Yeah, and they travel at different speeds through the glass. That's why it gets spread out. This is called dispersion. Dispersion, because they're dispersed. And that's how we get rainbows. The light from the sun will go into a water droplet, and the water droplet's like a prism. It refracts when it changes mediums, going into it and out of it. Spreads the different wavelengths, frequencies apart, and you see a nice, beautiful rainbow. But I like doing that with these colored projectors. Let's do it in reverse. There's some red light. I'm going to combine that with blue light because I have red here, green here, and blue there. Red light, when I add blue light to it, what do you expect to get? We're going to add different colors, different frequencies. Red and blue. Yeah, it's kind of a purpley color. That's called magenta. Magenta. What it's doing is it's activating the cones on our retina, our little sensors. So red light shines off of the white screen. It's reflected back into our eye, and it activates the cones that are sensitive to that frequency, which we call the red cones. Sends a signal to your brain, red. Blue does the same thing to the blue cones. So in your brain, this is activating the red and the blue cones, and we call that magenta when we see it. What do you think blue and green will give? Wrong way. Blue and green. We call this cyan. Cyan. So this light coming to your eyes is activating the green and the blue cones on your retina. How about red and green? Yellow. That's my favorite. So that activates the red and the green cones. So yeah, remember that. Next time you see anything yellow, it's activating red and green. And our brain processes it. All three together? White. Get white light there in the middle. It's composed of those three colors. We say all colors. Well, where's orange? Where's indigo? I like mauve, chartreuse. Well, our eyes peak at 3 main frequencies, red, green, and blue. So we say we got red, green, and blue cones. Color is kind of subjective. This is just frequency light going around, but we don't see color until it interacts with our cones. Yeah? Oh, that could just be how well I'm focused. Let's see here. Yeah. So I think that's what you're just seeing. But here's my favorite part. And I have to admit, this is my all-time favorite demonstration. There's other ones I agree are probably cooler, and I have more fun with. But the first time I saw this, I got more excited than anything else. It's the shadows. Doing. You can see the umbra, and you can see the penumbra, the fuzzy part on the outside, because these aren't point light sources. But they're not in the same spot either. Let's simplify here first. Red and green. If I block the green light, what do you expect to see there? Nothing. I'm blocking the green light, so it's black. No light's getting there to reflect off. Make sense? If I block the red light, black, because there's no light to reflect off. If I block the yellow, cool. So, what's happening? Well, this is blocking green, so only red makes it there. This is blocking red, so only green makes it there, because they're in different spots. Works with my hand too. Where they overlap, it's blocking both, and you get black. Okay. So, when you have all three, you tell me. We'll start with yellow. What color is being blocked right there? What colors make up yellow? Red and green make up yellow, right? So right there, red and green are making it to the screen. And overlapping, we see yellow. So I heard it. Blue is being blocked. You can think of yellow as not blue. Okay, which two colors are here on magenta? Red and blue. So magenta is not green. And cyan is green and blue, so it's not red. Isn't that cool? You can overlap. Look, I see green right here. So I must be blocking red and blue. They're overlapping there. What if, this sort of works, I take a, this is mostly red. You can't tell, right? Let's put it in the white, because that's all colors. Does it look red? Good. What if I put it in the red? What color do you think it'll look like? What color is this reflecting to your eye? Red. What colors is it absorbing? Green and blue, mostly. It's not a pure red. So that's why you only see red. It absorbs green and blue. The pigment resonates at the frequency of green and blue, so it gets absorbed, heats it up. Internal energy. It doesn't like red, though. So it's reflected back out. You see it. So if we hit it with only red light, it still looks red because it's reflecting that red. What if we don't give it any red light? Let's put it in the blue. What do you think will happen? See how it looks dark? Almost black? It's because it wasn't a pure red. It has very little... it's reflecting only red. But if you don't give it red to reflect, it looks dark. Should be something similar in green. Still dark. To me, it looks a little browner. So there must be some green in the pigment. It reflects a little bit of green, obviously. Let's try another color. There's yellow, mostly. So that's what it normally looks like. So if I put it in red, what will happen? What colors does this reflect? Red and green. So if I give it red, but not green, it looks red. It can only reflect the red. There's no green to reflect. And here it looks greener. Blue? Dark. Because it absorbs most of the blue. It only reflects red and green. That's how colors work in our lives. This is called adding colors, color mixing. These are, in my mind, the true primary colors. These are the primary colors of light mixing, when you add them together. It's when you start using pigments, paints and filters and cloth, they start absorbing and subtracting out colors. That's what pigments do. They filter out the color. Bright light. Let's show you that. All right. So I have magenta. What light's getting through this filter? Which two make up magenta? Red and blue. So this filter absorbs green. Its atoms resonate at the green frequency. They don't make it through. It's opaque to green. It's transparent to red and blue. Yellow lets red and green through, so it's opaque to blue. And cyan is opaque to red. So let's see, if I do a yellow and blue make what? You learned this as a kid, right? Your pigments. Yellow and blue make green. But the real primary color should be cyan. It's just, hey, little Timmy, can you say magenta? No, it's just, to a kid this looks blue. But we know it's cyan. So why does it look green? It's just filtering. Cyan stops which color? Red. Yellow stops which color? Blue. What's the only one that can get through both filters? Green. That's what's happening. So when you take a green crayon and write on your paper, it's absorbing red and blue and only reflecting the green. We put all three together. There, that's more symmetric. Good enough. So we just did this one, yellow and cyan, green. Yellow and magenta. Magenta lets red and blue, so it blocks green. Yellow does red and green. It blocks blue. The only one that makes it through both? Red. Same idea over here. Blue's the only one that gets through. And if you overlap all three of them, nothing gets through. They're all absorbed by one of the three filters, and you get black. That's why when you mix all your paints together, it's a yucky dark color. But for pigments, you can think of the primary colors as cyan, magenta, and yellow. But really, they're just using the primary colors of light and filtering out those to mix and match them. You should go look at the colored print in a magazine. Or get a magnifying glass and zoom in on your TV screen. Or a colored newspaper. What do you expect to see? These are pigments. Cereal boxes are fun. They usually print them on the flap. You'll see the colors of ink they used. They use cyan, magenta, and yellow. And you zoom in on it, you'll see the little pixels. Because when they combine, they're doing this game so that you can make any other color. Because they're filtering it. They're subtracting out colors of light. Yeah?
After your drama, can you explain how you did the thing yesterday when you recorded sound into
Oh, you're right, you're right. Okay, what do we got? 3 minutes? Okay. Yes, I'll explain that. While I got the lights off on this, though, let me finish this one. I made a picture of a parrot. Here he is. Isn't that gorgeous? You can see the yellows and the greens and the blues and the whites and the black. There's not much red by itself. But what this is made out of are 4 different transparencies. Yellow, well, you get the idea. Magenta, cyan, and they use black to help with the edges. So here it is in just yellow, magenta, cyan, black. So let's mix, I don't know, blue and yellow. Helps if you line them up, Adam. There we go. So this ought to give us yellow, blues, and greens. And sure enough, if we add blue with cyan with magenta, you can get some deeper blues. Let's put all those colors together. They can filter out and you get the original image. But we can block some for contrast. Add the black, sharpens up those edges. And that's how you can print things. It's just filtering out, subtracting colors that resonate or not with the pigment, the material. I think that's awesome. All right. I'll just get to do the other thing. So, at the end of the last class, those have cooled off. We did the music in the hoot tube. All right. I heat up the wire mesh. What's it do to the surrounding material? Heats it up, including the air. Hot air rises. There's convection. That's the causes the vibration. You get standing waves. It sings. It hoots. If I tip it, though, does the air still get hot? Sure. But what's it do? It's trying to go up, but it can't. It might get pushed out, but there's not much convection going on. The airflow is minimized. And if there's nothing driving it, there's no source of vibration. You don't get standing waves, and the sound just goes away. So I just pretend like I'm pouring it in a cup, but I don't need the cup. All I have to do is just tip it sideways. No sound, because there's no convection going. When I flip it back up, now the hot air can go, we get convection, and as long as it's still hot enough, it hasn't cooled off, you get sound again. That's all there was to that one. Clever, huh? All right, go read more of this color stuff. I will warn you that some of the homework and the test, you're going to have to know this interplay between colors and how to mix them. It's all laid out in your book. You know, when you add this color with this color, what do you get? When you subtract this color out, and the rest of next lecture will make sense if you already know that.